Classical probability gives us a straightforward and intuitive way to calculate the probability of some event. So we have the probability of event A is equal to the number of ways that event A can occur divided by the total number of outcomes in the sample space. Okay. But the problem here is that these are not always easy to calculate. So in a lot of cases they are. So for example, when the example that we looked at in the probability video, we were just interested in, okay, the probability of drawing a 3. So the probability of a 3 from a 52 card deck is going to be the number of ways of drawing a 3, which is just a 4, divided by the total number of outcomes that we could have had, which is 52. Okay, but when we have a problem set up like this, where the number of ways and the number of outcomes are easily counted, that's one matter. But there are plenty of situations where these are a little bit harder to compute. And so being able to count events is a crucial part of the whole business decision-making discipline. And I'll give you some examples of where this comes up. Now, sometimes the coming up with the counts has a value on its own, and then in other cases it's just part of the probability calculation. So here's some examples of problems that have come from previous final exams. So this is definitely the sort of thing that you would be expected to be able to do. So for example, we have 6 pallets and we want to line them up on a warehouse shelf. There is one optimal ordering that's going to minimize the amount of rearrangement that has to happen as items are picked off the shelf. So what's the probability that a forklift operator will pick the one perfect arrangement by chance? Okay, so basically we just need to find the denominator here of the number of ways of arranging 6 pallets. In this problem, we have potato chips that come in 2 textures, that is ruffled and plain, and 3 flavors, plain, vinegar, and barbecue, and 3 levels of salt, light, and normal. So if a manager needs to stock 4 of each kind, how many bags do they have to order? Okay, so how do we count that? In the next problem we see you have a staff of 20 and you need to pick a leadership team. How many ways are there to choose a manager and an assistant manager? So for example, if you were going to just rotate roles, how many different ways are there to set up that leadership team? And then finally, a classical problem of the traveling salesman. You've got a salesperson who has to travel to 5 different cities. How many different orderings are there for these 5 different cities? So, for example, if you wanted to, compare the costs of different tickets, airline tickets between each of these cities. So, if you wanted to just exhaustively try every single route, how many would you be trying, and how long would that take? Okay, so we're going to take a look at some counting rules that simplify these kinds of calculations. Now, there are innumerable different scenarios that you could have, and sometimes coming up with a count is very difficult. But if you go into these problems with a certain set of techniques or rules that you can start with, maybe you can recognize the problem as including some of these. So we're going to take a look at 5 different counting rules and give some examples of each. These rules, sometimes they come from games. Games of chance have taught us a lot about probability and about counting rules. Okay, so in some cases, I'll be making reference to games like this, but you should know that these are just toy problems that help to clarify how it works in the real world. Okay, but first, before we get into that, I want to just review something about multiplication. When we are trying to calculate probabilities of events that happen in sequence, we tend to multiply them together. And it's just called the general multiplication rule. General multiplication rule. And so why is that? So, an example of where we would do this is if we're just going to do a coin flip. So remember that the sample space for a coin flip is going to be heads and tails. And the probability of throwing a head is 1/2. So now what do we say? How do we do this? What is the probability of doing 2 heads in a row? Well, it turns out that it's just 1/2 times 1/2. And why is that? So it's 1/4. The probability of flipping a coin 2 times and getting 2 heads is 1/4. Well, let's take a look at this. Let's draw a tree or a ladder that shows how these things happen in sequence, and I think it'll clarify why we do the multiplication. So if we think about each flip as a branching point where we can either go to a head or a tail, and each of these is a 0.5 probability, then we can see quite readily after this first step that we have, the probability of just h is 1/2. But now if we do another throw, we've got another branching point where, again, with 0.5 probability, we could go to heads or tails, and here heads or tails. So if we're throwing twice, we have 4 different paths. We could go down this way, and then this way, and then wind up with heads and heads. Or we could go down this, that is, we throw a head and then a tail, so we wind up with head and tail. We could have thrown a tail first and then a head, wind up with tail, then head. Or we could have thrown a tail and then another tail, so we have tail, tail. Okay, so we can inspect these 4 different outcomes, and we can see that one of them includes the case of 2 heads, which is exactly what we calculated with the shortcut right here, 1/2. Okay, so when you have probabilities that are executed in sequence like this, and each step is going to be a branching, and you have consistent probabilities that go from one step to the next, then you can just multiply these probabilities by each other. Okay, so we're going to see that in action as we go through some of these counting rules. Okay, so as I said, there are 5 counting rules, and we're going to just go through them one by one. Okay, so counting rule 1 has to do with a case like this one. If we were to roll a die 4 times, how many different rolls can we have? Okay, so we could just roll all 4 at the same time. So if we roll the die 4 times, how many different rolls can we have? Well, if we think about each roll as being like a blank, let's say. So with each roll, we're filling in one of these blanks. And we can think about, well, how many different possible values are we going to have in here? Well, it's 1, 2, 3, 4, 5, or 6. Okay, so there's 6 different values. And with that second roll, we also have 6 values. And with the third roll, we have 6 values. And with the fourth roll, we have 6 potential outcomes. So this is 6 times 6 times 6 times 6, or, the shorter way of putting that is 6 to the 4th. Okay, so the formal statement of this principle is if any one of k different mutually exclusive and collectively exhaustive events can occur on each of n trials, the number of possible outcomes is equal to k to the n. Okay, so that's a little bit of an opaque way of putting it, but if we think about this example, we have we can think about each of these slots as a trial. So these are our trials. And so we have, in this example, we've got k equal to 4. 4 different trials. And the other number that we need is, n trials. That's our n. N different trials. And so we've got k different mutually exclusive and collectively exhaustive events. Okay, so are these mutually exclusive and collectively exhaustive? Well, you can't roll a 2 and a 3 at the same time. So these are all mutually exclusive. And they are collectively exhaustive because there's only 6 of them. So there's only 6 possible outcomes. So then our k for this problem is equal to 6. So then the solution as stated is k to the n. So here we have k to the n, which winds up being 6 to the 4th. Okay, so but I think it's a little bit easier to just think about it as, each of these die throws as being a blank that you can fill in 6 possible ways, and you wind up with the number of different possible outcomes to the power of the number of different trials that you have. Okay, so counting rule 1. Let's take a look at an example. So what's the probability of randomly guessing this lock on the first try? Okay, so take a look at this lock and take a look at this problem, and go ahead and pause the video and see if you can figure that out. Okay, so there are 40 different possible numbers. So our sample space here has 40 different potential events. So this is our k, and they are mutually exclusive and collectively exhaustive, so that's going to be 40. And our n, well, I didn't state this in the problem, but I would hope that you'd know by now, after having been to middle school and high school and having had to go to gym, that these take 3 different numbers. So n is 3. So you can think about this as, okay, well, there's 3 different trials right here, and each of these can be filled 40 different ways. And the reason it's 40 for all of them is because we can have a combination that's just 5, 5, 5, 10, 10, 10. So repetitions are allowed. So we go ahead and use this rule. We just multiply these together. 40 times 40 times 40. Okay, so, or 40 cubed, or k to the n in the terminology of counting rule 1. Okay, so 40 to the 3rd. Let's just, I'm curious how big that number is, so let's go ahead and try it. 40 cubed. Okay, so there's 64,000 different possible combinations, and we can, we just do 1 over that answer to get the probability. Okay, so it's a very small probability that you're going to guess this lock combination on the first try. So it's 1 over 64,000. Okay, so let's go on to counting rule 2 then. So counting rule 2 is designed to help you deal with situations like this. So let's say we're going into Subway and we're trying to put together a sandwich. And we've got 3 choices of bread, 2 choices of meat, and 2 choices of cheese. How many possible sandwiches are there? Okay, so once again, we can do this whole filling slots thing. So we'll say, okay, we're going to have this is going to be a meat slot, and this is going to be a cheese slot, and or we could say, it doesn't matter what order, because multiplication has the commutative property. So meat, cheese, and bread. So these will be our different slots. So let's see, how many different breads do we have? We've got 3 breads, and we've got 2 meats, and we've got 2 cheeses. Okay, so we've got 12. 3 times 2 times 2 is 12. So 12 different possible sandwiches. So this is counting rule 2, which, remember, just, well, let's go ahead and take a look at the formal definition of it. Okay, so counting rule 2, as it puts it in your book, if there are k sub 1 events on the first trial, so you can think about each of these slots as a trial. So there's a meat trial, a cheese trial, and a bread trial. K sub 2 events on the second trial, ... K sub n events on the nth trial, then the number of possible outcomes is just the product of all of those. Okay, so we had, in our case, K1, we had 2 different kinds of meat. K2, we had 2 different kinds of cheese. And K3, 3 different kinds of bread. So we just did K1 times K2 times K3 and wound up with 12. Okay, so let's take a look at another example of this sort of problem. Okay, so this one was introduced at the beginning of the lesson. So go ahead and see if you can come up with an answer for this one. So go ahead and pause the video and we'll come back in a minute. Okay, so we've got 3 different, once again, 3 different slots to fill. We've got 2 different textures. So this could be our texture slot. 3 different flavors, so this could be our flavors slot. And 2 different levels of salt, so this will be our salt. So we had a 2 in here, we had a 3 in here, and we had a 2 in here. Okay, so the number of different possibilities is just going to be, this is just going to be 12 again. We happen to have the same numbers in both problems. But take a look. Notice that if the manager has to stock 4 of each possible kind, so the answer to this problem, of course, is actually going to be 4 times that, so 48. Okay, so counting rule 3 gives us a way to calculate how many different ways we can rearrange something. So in this example, how many orderings are there for 5 students to walk through a door? And once again, if we use our old technique of thinking about each of these positions going through the door as, we can imagine like blanks on the floor here where we're putting students in. We can say, okay, well, from this group of 5 students, we can pick one to go in this first position. So let's say the door is right here. And how many different ways are there to pick that student? Well, there's 5 students, so it's 5. So then we have to pick, a student to go into the second slot. And this time, we don't have 5 available anymore. There's only 4 available. And so by the same reasoning, we've only got 3 left here, 2 left here. And then by the time we get to this last slot, we've only got 1 guy. So we don't have any more degrees of freedom there. We just we just pick that one. And once again, we are multiplying these all together. So we wind up with 5 times 4 times 3 times 2 times 1, which is denoted, a shortcut notation for this is 5 exclamation point or 5 factorial. And so you have the factorial function available on your calculators, although it's not as easily found as it is on some other calculators. So in this example, we're going to do 5 factorial. We put in 5, and then we have to go to, let's see, math, come over to probability, and then scroll down here to this exclamation point. So we got 5 factorial, and so that's 120. So there's 120 ways for 5 children to go through the door of the classroom. Now, the amazing thing about the factorial function is that it grows unbelievably fast. So if we had, say, a class of 10, and I'm going to do this rather than doing it on a calculator, which actually can't handle values this large, I'm going to use the Wolfram Alpha computational engine. I don't know if you've used this, but it's basically a website that is a big calculator that can do some quite amazing things. So so we did factorial of 5, and that's not hard. So 120. If we were to say, okay, well, now we're up to 10 students. Okay, so look how quickly this grew. We're already up to 3.6 million. And if we were to say, okay, typical size class at Radford is 36 students, so factorial 36. So if we were to say, okay, 36 students, how many different orderings are there for you to come into the classroom? So it's this number right here. So factorials, you have to be careful about doing too much with the factorials, because it grows really, really fast. Okay, and the next 2 counting rules will involve factorials, so that's why I start with that caution. Okay, so here's the official wording of this rule. So the number of ways that n items can be arranged in order is n factorial, or n times n minus 1 down to 1. Okay, and so the business example of where this problem comes into place is our old pallets. How many different ways are there to arrange 6 pallets on a warehouse shelf? Okay, so now that you've got that counting rule, go ahead and pause the video and figure out what is the probability of a forklift operator picking the very best arrangement of these 6 pallets. Okay, so it's just 6 factorial. That's the number of arrangements, and so the probability would be 1 over 6 factorial. So very quickly, just for variety, let's go ahead and calculate it in Excel. Excel will also let you calculate factorials. It's just fact, and then there's only a single parameter, so it's like this. Okay, so 720 different arrangements of 6 pallets. So the probability of picking the optimal one just out of random at random is 1 over that. So you see it's very small. It's 0.1% that he's going to do it right, just using luck alone. Okay, so there's counting rule number 3. So counting rules 4 and 5 are getting into something that you've probably done before, which is permutations and combinations. These have to do with selecting a subset of items from an initial collection of items. We'll do permutations first. So and I'll explain why in a minute. So counting rule number 4 teaches you how to answer the question, how many ways are there to arrange 3 books from a set of 5? Okay, so if this were just rearranging 5, we already know how to do that. That's 5 factorial. But this is asking us to first select 3 and then to arrange them, and how many different ways are there to do that? Okay, well, whenever you see an arrangement and there is some subset taken from a superset, this is going to be a permutation, which is denoted with a P. And the permutation function takes 2 parameters. It takes n and x. Okay, so what are these? You'll sometimes see this abbreviated, say, on a calculator as n PR x or something like that. But there's always this big P in here, and then the 2 parameters on each side. So n is going to be the size of our original set. So in this problem, that's 5. And our x, usually x is used for the actual value that you're asking about. So we're going to take a subset of 3. So what we're actually looking for is the answer to 5 permute 3. Okay, so this is a notation, but it doesn't really give us any way to calculate that. Okay, I'm going to give you a formula first, then show you how to calculate these both on your calculator and in Excel. So the formula goes like this. It is n factorial divided by n minus x quantity factorial. Okay, so let's go ahead and plug in the numbers, and then in a little while I'll show why this makes sense. So so our n we said was 5, so 5 factorial, and then so n is 5, x is 3, so 5 minus 3 is 2 factorial. Okay, now let's go ahead and show you a little trick that you can use to calculate these. So we've got 5 factorial. 5 factorial is equal to 5 times 4 times 3 times 2 factorial. And it turns out we have this over 2 factorial already. So those will just cancel. And a lot of times this sort of cancellation trick will come in handy so that we don't have to compute these enormous factorial values. So we've got, 5 times 4 is 20 times 3 is 60. So the answer to this problem is 60. 60 ways of permuting 3 books from a set of 5. Okay, so on the next slide, we see again the formal articulation of the problem that I gave you, and hopefully it's a little bit clearer now than it was just on the slide. So we talked about what n was, what x was, and how to do this factorial. Okay, so this is our permutation. Let's take a look at a problem where this comes up. This again was a problem that we saw on the first slide. You have a staff of 20 and you need to pick a leadership team. How many ways are there to choose a manager and an assistant manager? Okay, so if you think about this, we have an initial starting set of 20. So we've got n is equal to 20, and we need to pick a manager and an assistant manager. So we're just going to have these 2, and we can think about, well, we're going to pick 2, and then we're going to, the order matters here, right? Because one is going to be the manager and the other one's going to be the assistant manager. So what this is asking us to do is do 20 permute 2. Okay, so x is equal to 2 here. So again, the problem here, the formula here is n over n minus x factorial. So we got 20 factorial. And now, so n minus 2 is 18 factorial. Now, rather than put these into a calculator, let's do the cancellation thing. So we're going to do 20 times 19 times 18 factorial divided by 18 factorial, and those 2 cancel. So it's just going to be 20 times 19, which is just going to be 380. Okay. All right. So in contrast to permutations, we also have combinations. Now, combinations do this similar thing where they're taking a subset of something from a larger set, but in this case, order does not matter. So there are plenty of cases where you're just concerned with how many ways are there to pick something, and you don't really care what order they're in. So in this case, we're asking how many ways are there to pick teams of 2 from an office of 25 people. Okay, so this time it's just a team. So the order doesn't matter. We're just picking 2. So we can say the way to state this is 25 choose 2. And sometimes you'll see this written as 25 2 in parentheses like this. Okay, and then likewise in the other notation where we had the big P in the middle, you'll see big C in the middle. And once again, we have these 2 parameters where we're going to have 25, so this is our n, and then choose 2, so this is going to be our x. So the problem now is 25, choose 2. So we can expect this problem bears a lot of similarities to the permutation problem. So we would expect the formula to look really similar, and it does. We start off with the n factorial in the numerator, and we actually, once again, have the n minus x factorial in the denominator. But then we also have something else in the denominator here, which is another x factorial. Now, so which is going to be larger, 25 permute 2 or 25 choose 2? Okay, so if we don't care about ordering, then we're going to have twice as many combinations as, we're going to have twice as many permutations as we have combinations, right? Okay, so because if you pick, if you pick person A and B, and then person B and A, if we don't care about orderings, these are the same, so that's just 1. But if we care about the permutations, then that's 2. So the number of permutations will be larger than the number of combinations. So we have this little thing in the denominator here, which is going to bring that down. Okay, so let's go ahead and look at one more example of this, and then I'm going to explain the relationship between combinations and permutations. Okay, so there again on this slide is the formal statement of this formula. So again, we've got n choose x, and there's the formula as I put it. We've got our number of items. We've got our the same thing from the permutations, the difference between the starting set size and the subset, and then that x factorial there. Okay, so okay, so let's take a look at this problem then. So if everybody in a room of 12, so we've got 12 people in the room, has to shake hands with everybody else, how many handshakes will there be? Well, this is really just asking us 12 choose 2. Okay, and so the formula then, or we could just write it 12 choose 2. So this formula, and I'll just write it again real quickly, n factorial over n minus x factorial x factorial. Okay, so this is our n, this is our x. So we're going to have 12 factorial, and then n, which is 12, minus 2 factorial, so 10 factorial, and then x, which is 2 factorial. Okay, so we'll do that cancellation trick again. 12 times 11 times 10 factorial over 10 factorial, 2 factorial. These will cancel, so this gives us 12 times 11 over 2 factorial. 2 factorial is just 2 because it's 2 times 1, and so this will cancel with this, so that'll just be 6 times 11. So that'll be 1, and we'll just have 66. Okay. You can find permutations and combinations on your calculator. I'll show you how to do them on the calculator as well as on the in Excel. So let's go back to the permutations problem where we were finding, let's say this one. So 20 permute 2 on your calculator. Let's turn this on. So it's an infix operator, meaning that you have the operands on the outside. So we're going to do 20, and then we're going to come back here to math and probability again. Now see, there's that NP, and they're using R instead of X, but it's the same thing. So permute, and then so we've got the 20 here, and then the permute operator in here, and 18. Okay, and no, sorry, that should be 2. So let's do 20 permute 2. Okay, and that's the answer we got. Okay, so let's do the combination problem in there too. So when we did our combination problem, we had 12, choose 2. On your calculator, you can come here and do 12, and then do math, probability, NCR, choose 2, and that's 66. Okay, now, so how do we do these two problems on Excel? So we had 20 permute 2. So on Excel, you're just going to do equals, and then the name of the function is PERMUT, and then 20, comma 2. So 20 permute 2, and that's the answer we got. And then we had 12 choose 2, and in Excel, that is so COMBIN for combinations. So we had 12 and 2. Okay, so it gets the same answer again. Okay, good thing. Okay, so there's our five counting rules. So just to flip through them really quickly again as a bit of a review. So remember that in counting rule 1, we had these k mutually exclusive events, and we had these n trials. So we're doing k to the n. In counting rule 2, we had different numbers that we multiplied together. Okay, this is the sandwich example. Counting rule 3 had to do with ordering something, and counting rule 4 was permutations, and counting rule 5 combinations. Okay, so now that you have those, let's take a look at a few of the problems that are there on your homework. And I'm not going to solve them all the way, but I'm just going to show you how you can go about applying these rules and how to recognize when a problem is an instance of one of these. So, okay, if there are 19 multiple choice questions on an exam, each having 2 possible answers. Okay, so 19 multiple choice questions, each having 2 possible answers. How many different sequences of answers are there? Okay, so we could, if we wanted to, draw 19 different blanks, but just imagine there's 19 of those there. So we got 19 different blanks, and each of these questions has 2 possible answers, right? So that's 2, and that's 2, and that's 2, ... So they're all 2s. So this winds up being 2 to the 19th power. Okay, and this is rule 1. Okay. A particular brand of women's jeans is available in 5 different sizes. Okay, let's start highlighting these. So 5 different sizes and 4 different colors and 3 different styles. Okay, so how many different jeans does the store manager need to order to have one pair of each type? Okay, so we've got a size blank, and we've got a colors blank, and we've got a styles blank. Okay, so let's see, this is going to be 5 and 4 and 3. Okay, so 20 times 3 is 60. So the manager has to order 60 of those. And this, you'll recognize, was rule 2. Okay, let's take a look at a couple more. A team is being formed that includes 7 people. Okay, 7 different people. There are 7 different positions on the teams. How many different ways are there to assign the 7 people to the 7 positions? Okay, so we can think about it this way. So we've got this team. It doesn't tell us what kind. Let's say it's a baseball team. Let's say we've got a pitcher position, we've got a catcher position, first base, second base, third base, 1, 2, 3, 4, 5. 6, 7. Okay, and then fielder and shortstop. Okay, so there's 7 different positions here, and we're going to assign these 7 people to these 7 positions, right? So remember that when we're doing this, we have 7 people to choose from for this one, and 6 for this one, and 5 for this one, etc., on down to 1, and which is 7 factorial. And just in the interest of, for my own curiosity, I want to see the magnitude of these numbers, so let's go ahead and do that. Factorial of 7, 5040. Okay, so there are astonishingly, over 5,000 different ways to put 7 people on a team. Okay, it's just amazing. Okay, so last one then. A student has 13 books that she would like to place in her backpack. However, there is only room for 11 books. Okay, regardless of the arrangement. Okay, so regardless of the arrangement, what is that going to tell us? So we know that order doesn't matter. And which is it that you use if order doesn't matter? Permutations or combinations? So it's combinations. So how many different ways are there of placing 11 books in her backpack? Okay, so we've got 13, and she just needs to choose 11. Okay, or we could put it 13, choose 11, and we'll let's go ahead and do it in Excel again. So this is a combination. So we'll do COMBIN, combination 13, choose 11. So 78. So 78. 78 different ways. Incidentally, if we were to ask how many ways are there of choosing 13 books? Right, so it's 13, choose 13. Well, there's only one. There's only one way to do that, right? You just choose all 13. What if we were to say, okay, what's 13, choose 1? How many ways are there of choosing one book from 13? Well, that's just 13. Okay. On this issue of permutations and combinations, I want to show you one more thing, which I think will highlight the relationship between permutations and combinations a little bit better. So remember that when you do a combination, or when you do a permutation, let's say, permutation. So let's say we're doing that backpack, or we're doing that book problem where we had 5 permute 3. And the formula for that was n factorial over n minus x factorial. So one thing we could think of, a way to think about this problem is, let's say, okay, this is actually 2 different tasks, right? We first have to pick 3, right? And how many ways are there to pick 3? So now that's just 5, choose 3, right? So once you pick that 3, then that is it's a combination, and its formula is n factorial over n minus x factorial times x factorial. But then once we've chosen the book, and this is very messy here. Once we've chosen the 3 books that we have, then the next step is we have to rearrange them, right? So we've got the 3 books, and then we have to order them, right? And that is nothing more than x factorial, right? Or 3 factorial. So notice what happens here is we multiply this by this, and we see that these cancel. Okay, so if you think about a permutation problem as actually, first you select the subset, and that's going to be a combination problem. Then you have to rearrange them. That's going to be a permutation problem. Then suddenly this permutation formula makes a lot of sense, because all you're doing is doing this two-step and then canceling the x factorials. Okay. All right, so there are a few counting rules, and I hope those will help you solve the homework problems. And as always, please let me know if you have any questions or problems.